Oops. Okay, so this chapter we're going to talk about what you do with all the nutrients that you have bothered to break apart with the enzymes starting in the mouth, with amylase and then pepsin in the stomach, and then amylase and trypsin and chymotrypsin, carboxypeptidase, lipases, nucleases, all produced by both the intestines and pancreas to help make sure that the food that you are consuming, again, we think of this as your macronutrients because they have a fate, and then your micronutrients have a fate, right? Now, the micronutrients, you'll find out in this chapter, you don't break down. You never developed enzymes for these. There's no need for that. You're not taking them apart for energy. You're not taking them apart to use them specifically as a building block, with a few exceptions, obviously, like iron and hemoglobin, but the iron itself is not changed by this process. So, anyway, focusing here on those big, right, the big three, proteins, carbohydrates, and lipids, we want to think, now we've got all these amino acids flooding our blood, right? You've got your carbohydrates all converted to fructose, galactose, and glucose, and you've got your lipids, which we consider dietary lipids, fats and oils, are all now in the form of fatty acids and monoglycerides. So what do we do with this? All right, so way back in chapter 2, in chapter 3 of AMP1, we told you about, well, look, there's all these different chemical processes that keep you alive, but they really come into these two groups. They come into groups we call synthesis or synthetic reactions, and then we have these catabolic or degradation hydrolysis reactions. And they center really around this molecule ATP, which is the only form of chemical energy we can use. All right? So I'm saying that, those calories that you recorded in your nutrient recall, and as you look at your labels, these calories represent this idea of how much energy is contained in the bonds. Should I take this apart to its completion, right? Just totally take apart all the carbons, hydrogens, oxygens. How much would I get? All right? And remember, I'm going to transfer that to ATP, and then I can use that ATP. All right? Well, then we don't use everything for energy, right? Back in chapter 2, we said, well, your carbohydrates and your lipids, especially fats and oils, are predominantly used for energy. Your proteins generally have other fates, though they can be used for energy. So, because you do get calories out of them, as we discover in this chapter. All right? So, the energy fuels, right, all the synthesis reactions, which is what we do a lot with our amino acids from our proteins. So you ate these proteins, you broke them down to amino acids. Now what? Well, you're going to make new proteins. You're constantly need a hemoglobin, collagen, elastin, antibodies, all these things we've talked about throughout both these courses. You use a lot of these proteins to build new cells, so epithelial cells and connective tissue cells always undergoing mitosis. And ultimately, these cells are conformed into new tissues, so body parts. And then you can recycle stuff for your needs as well, right? So here's, again, this is the idea of what's the fate of all this chemistry, all right? So the term metabolism, which you might recall is a characteristic of life, right? Anything that lives has to be able to metabolize, is basically all the chemical reactions and pathways, so numerous chemical reactions that make up a pathway, which allow this to happen. You can build the things you need when you need them. You can take apart the things that you have when you need to be able to power the energy, find that energy to power your synthesis, because that is how it works, right? What we're going to call your catabolic here shortly, the destructive and take it apart, release its energy, basically power the synthetic, what we call the anabolic. So, again, anabolic pathways are synthesis, building things up. Catabolics are breaking it down. And they are coupled by energy, with the catabolic releasing energy, devoting it to or transferring it to ATP. And then the ATP is used in the anabolic pathways to do all the synthesis you need. Whew. All right, so metabolic reactions. I say, the first thing we have to embrace is that you spend your life between these two physiological states, feast and famine. And that's a given, right? And because energy is required for everything on this planet, and we are focusing on you, and you are in constant needs of energy, right, as you guys are determining your basal metabolic rates, and then you're adding additional activities, you need energy all the time. So you live between the states of when you are receiving a lot of potential energy and when you don't have much. All right? And I said it's really important to wrap your minds around this. And it's all about survival, which depends on energy and how we use energy. All right? So again, catabolic reactions release energy, anabolic reactions use energy. And I say, theoretically you break even, which is why we talk about balance and why we look at balance in your nutrition recall. All right? If more energy is released, catabolic, than is used for immediate needs, right? Any of your building that has to go on right now, I absolutely got to get this cells together, I got to make this much hemoglobin. I said any excess energy is stored, typically as fat. So first, if it's carbohydrate, we store it as glycogen, but we only have so much capacity for glycogen. We have lots of capacity for fat. And fat is a potential energy molecule. All right? If you need more energy, and think again for your anabolic reactions, so if you need more than is released, you will tap into these energy sources. So again, that's your famine. So here's your feast state, here's your famine state. All right, so let's look at these catabolic reactions. What do they entail, right? So we break down large organic molecules into smaller ones. So you thought you were done in digestion. No, this glucose, galactose, and fructose comes in, and it's going to be broken down farther. And you know this, right? You know that we haven't stopped with this. We don't use glucose to build, specifically incorporate into molecules. We use it to take it apart and get the potential energy out of it, right? So this is... right? Ideally, the energy is transferred, right? Because fundamental laws of physics say you can't create or destroy it. And to be purposeful, we have to transfer that potential energy we measure as calories into this molecule, adenosine triphosphate, right? Now, ATP, a lot of people, because we're not familiar with this, and here, again, just trying to show you a crude cartoon of what it looks like. ATP is a temporary, it is not a stable molecule, right? So all these negative charges give you a hint as to why it's not stable, right? But it is the only form of energy a cell can use. It's a very small molecule. It fits in a lot of places on other molecules, and when it does, and it falls apart, it causes things to happen, right? Because the term energy is the capacity to do work or make change, and this little molecule suits that very well. So ATP will drive these anabolic reactions, so we're going to use it for our synthesis, right? So here we go. Energy, we'll put anabolic reactions, store energy, release from catabolic reactions, all right? So we're going to ATP will drive anabolic reactions, drive all synthesis. All synthesis takes energy. Muscle contraction, electrical potential, right? Moving those sodiums, potassiums, calciums, and movement of molecules in general. So this was like our co-transport, our active transport. We did a lot of that, right? As we talked about absorption even. And endocytosis, exocytosis. Those are all energy needy, energy dependent, all right? So I say, what can we break apart to get this ATP? Well, it turns out a lot of things. We're very good. Biochemically, we've evolved to a really good position in life, meaning that we're not dependent on a specific food group to continue existence. Say, for instance, pandas and polar bears. I mean, that puts them at a disadvantage. And one of the reasons why, of course, they are in the endangered, listed as endangered. So here we go. Again, you get a whole mixture of different foods you take in, all of these containing calories, and the calories are basically measured fairly precisely by a laboratory, and that number is telling you, well, what happens, how much of that can I get out of this molecule, all right? So, and then the proteins have one metabolic, these arrows represent many metabolic pathways too, by the way. So this is a very, very simple cartoon to represent a very complicated thing, but that's okay. We don't have to be complicated, all right? So in your protein, in your food groups, there's proteins, and proteins are in a lot of things. I mean, people make this assumption that, oh no, it's animal products. No, plant tissues are made of proteins. For gosh sake, you get a lot of proteins from a lot of things that you eat if they were once living, right? And you even recycle proteins from your own cells as they die off, especially in the digestive tract, and the mucus that you swallow all the time. Okay. Complex carbohydrates, because that's what we recommend that you ingest quite a bit of in your diet. And that's also found in a lot of things, including the fact that meats, right, store their carbohydrates as glycogen, right? And of course, there's it's not complex in milk, but complex carbohydrates are also on the food labels for that reason, so you're aware of that. It includes fibers, and it does include, carbohydrate label includes all carbohydrates, but we really recommend complex, large, big ones, all right? And then triglycerides, so fats and oils. Right, so this glycerol with these 3 fatty acid chains. All right. Well, again, all this food has calories, and we need to be aware that it doesn't matter what it is. We're not going to assign calories to vitamins. We're not going to assign calories to minerals. We don't assign calories to nucleic acids because we do not take those building blocks or those molecules apart to release energy and capture it in the formation of ATP. All right. I said, while we can use a lot of organic molecules to release ATP, the most common will be the carbohydrates, which is one of the reasons why we recommend a high consumption of, again, complex carbohydrates. All right? All carbs do become glucose. So that's why we only talk about your blood glucose levels, not your blood fructose or blood galactose or blood sucrose, yada, 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 right? And you might recall how carefully we managed this from the chapter on endocrine, right? We devoted quite a few hormones to trying to maintain glucose levels in our blood. And I said back in that chapter that we do this because the nervous tissue absolutely requires a certain concentration of glucose in order to keep functioning. And many, many, many tissues use glucose to manage their energy needs. Right? So again, this is a really simple but good cartoon that shows you here's what you've consumed, right? Here's what it's comprised of. It's been digested, so this is all showing you this idea of what happened in the process of digestion. And then here's the fate, right? Amino acids are made for a whole lot of different protein synthesis. It just remarks that we do cannibalize our own muscle tissue, and this happens if you don't take in, again, you're in a prolonged famine state. Glucose is predominantly used for energy production. That is its role. All right. This is showing you again that there's storage of glycogen, which is a type of carbohydrate, in liver and skeletal muscle, and this can be tapped into when I'm in a famine state. Triglycerides, basically broken down by the lipases to glycerol and fatty acids, are often stored, if not immediately used. We have a really good, efficient way to store these in a high capacity. So, and this would, of course, happen during our feast state. You can break down those fat stores and convert them back and then use them for energy production if you need to. This again shows you that amino acids can be used for energy. Glycerol fatty acids can be used for energy. So a really nice, simple cartoon that really gives you the big picture. All right? So lipids, triglycerides, fats and oils are used through beta oxidation, and this happens during famine, right? Typically, we're not going to break down our fats and use them for energy if we have plenty of carbohydrates and plenty of a mixed diet. And stored in the adipocytes when it's feast, okay? Amino acids from proteins are usually made into new and useful proteins, but can be broken down, as we show in this pathway, to release energy if you are in famine. All right? So here, the anabolic reaction, so that we're really focusing mostly on the catabolic, says that, yeah, you can make these, right, molecules if you so require. You make whatever proteins you need, and that's traditionally you make glycogen and you make lipids when it's needed. So this is kind of showing you this idea during the anabolic reactions is like green, right, as I show you down here for the key. All right, so smaller molecules are joined together to make larger ones, back to the proteins and back to the triglycerides. Glucose is stored as glycogen and fat. Yes, if you have excess carbohydrates, it goes to fat. Fatty acids are joined to make triglycerides and stored. Amino acids make proteins, and of course nucleotides make nucleic acids. So this is all part of that, again, anabolic reactions. Part of you have plenty of energy. Here's what I'm going to do to hold on to it and keep it. All right? So this is a good start. We will continue on this in the next video.